Okay, I'm going to go ahead and get started for the introduction here. So, welcome to the NCSA Colloquium Series. We work hard, as I say every time, to bring in great speakers, and I'm really pleased that Shantenu Jha has come today from Rutgers University in this tradition of great speakers. Shantenu is an old friend and colleague. In fact, I realized that I first met Shantenu when I was at NCSA years ago, and Shantenu showed up as a potential incoming graduate student here. So, and we sort of encountered each other then, and then I moved to Europe, and then we began to encounter each other there a lot as well. And so, he's a very interesting figure in our community, and I think is a kind of an exemplar for what you see in the community these days. People with backgrounds in different areas of science. Shantenu is a physicist, and perhaps you might think of yourself as a biologist as well, and also as a computational scientist, and it sort of exemplifies the convergence of all of these fields and sort of into the new areas of science and engineering that are emerging. So, Shantenu is a professor at Rutgers University in computer engineering and a radical researcher. Or radical actually he's not been radicalized, but he is research in applied distributed computing and applications laboratory. So there's a laboratory with this name. His research interests lie at the triple point of cyberinfrastructure research and development. So of course there's a research agenda around development of cyberinfrastructure, applied computing, and computational science. His research is currently supported by DOE and NSF awards, including a career award from the Division of Advanced Cyber Infrastructure at NSF. Those are very prestigious, very hard to get awards. It's not surprising Shantenu has one of them. SI2, which are the software institutes, and including elements integration and conceptualization, CDI, and EarthCube. He's been involved in many activities. In fact, also Shantenu and I worked together at the Center for Computation and Technology in Louisiana for a few years, where he was leading a research area called the Material World, which is a cross-cutting area of developing everything from material science and chemistry to biology, computational biology, developing the tools and so on. And today he's going to tell us about how these things all come together in a talk entitled Expeditions in Applied Distributed Computing and Towards the Science of Cyber Infrastructure. Thanks, Shantenu.
Thank you, Ed, for that introduction, and thank you, Gabrielle, for the invitation. It's a pleasure to be here. The title is slightly vague. It doesn't clearly state what I'm going to speak about, and in a way, there isn't a hypothesis-driven research agenda here. And the Expeditions is a label of trying to tell you, convey to you, what has been a process over the past 10 to 12 years of working in distributed computing. And I know Gabrielle won't be here towards the end, but in a way, this expedition began very much at the CCT, the seeds of which were laid right there, and it's been hopefully a rewarding journey. But it's only the beginning, and what I hope to show you is some of the seeds that were laid by the vanguard experiments and papers which won the Gordon Bell Prize back in 2001 or 2002, the cactus worm. These are ideas that have taken 12 to 14 years to materialize, to take those initial conceptual, literally breakthrough ideas and try to make them something which I like to say, taking the impossible and making them possible, and making the barely possible routine. I hope I can convey that, and this is, as any good expedition should be, just a checkpoint, and where this expedition, I hope, will lead us all is towards the science of cyber infrastructure, which I'll talk about more towards the end. So what I have here is a collage of science applications that I've worked on over the past, let's say, decade or so. A lot of them have been at the interface of biology and chemistry, but there've also been some in the middle towards more hydrometeorology and climate sciences. And then over the past couple of years, working with the Atlas project responsible, as many of you know, for the Higgs boson. And the point really here is that something which I think I don't need to tell this audience, that high performance and distributed computing, and I will use the high performance distributed computing as a whole, is fundamental for supporting the large range of science and engineering projects, problems that that the community is interested in. And without a doubt, it's important for the big projects, the LSSTs, the Higgs bosons, but it's equally important for the long tail of science. And I think what the grand challenge really is, if there is a grand challenge, is to be able to design cyber infrastructure that meets the requirements of the entire spectrum seamlessly. And so as problems start off small and grow, there isn't major refactoring. But there's another grand challenge, in my opinion, maybe not as grand, but something that is critical in the road towards using the collective cyber infrastructure effectively, efficiently. And that is the ability to be able to use distributed infrastructure in an effective way so that you're not pinned to a single resource, you're not pinned to a platform, and you're able to use all the infrastructure in intelligent ways, i.e. the whole is greater than the sum of the parts. And I'll refer to this aspiration, the whole is greater than the sum of the parts, as the collective utilization of distributed infrastructure. And I'd like you to keep that in mind. Just maybe a 30-second detour before I move on to the next real meat of the work. This is obviously working with application scientists and appreciating the science, but it's as much about building the tools, the technology, and the infrastructure. And this is what I mean by working at the triple point. You have to appreciate the science and often define the right abstractions in the tools. And I'll hopefully come back. And the bottom layer is a representation of some of the tools that I've developed along the way, my team and I. And hopefully you'll see the convergence, the co-design. Okay, so here's the, if you will, the grand motivation. And I hope nobody will take offense to this because it is meant to be very complementary, that although we've made great strides in high-performance distributed computing, in provisioning infrastructure like the TeraGrid and Exceed, and we've supported great science. The Higgs boson is just one of the many examples. We are still learning how to architect large-scale production DCI being distributed cyber infrastructure. And I'm going to present this along three, if you will, circumstantial cases. The first is that minor differences in distributed computing infrastructure DCI requirements and, if you will, basic technologies leads to drastically different endpoints. This chaotic sensitivity to initial design requirements or initial science requirements is indicative of a problem. So the slide before you had Exceed and you then have OSG. To users of these infrastructures, they appear very different. They are very different, obviously. But my question to you is, do they need to necessarily be very different? Obviously, at some level, they have to be different because the resources being federated are distinct. We have Exceed as a federation of extremely large machines, and OSG, as many of you know, for the most part, is a federation of smaller machines and a much larger number. So clearly there are details that will determine the distinction in the mode of federation. But at a service level, at a conceptual utilization level, do they have to be different? My argument is if we had the right design principles and abstractions, they would be, if not entirely similar, less different. The second circumstantial evidence that I provide in support of the case that we are still learning is that distributed applications, of the few that exist, are either trivially simple or they are glued to a specific platform, and it's very hard to move them around. This often leads to situations where when you do try to move them around, they're brittle, bespoke, and kind of very fragile in the sense that you have to refactor them once you try to actually move to a new platform. This again points to, I presume you'll see the connection to the first point, to the lack of infrastructural abstractions, because if we had those infrastructural abstractions, there'd be less of that fragility. And I will try to give examples of all of these. And the last, and I think probably in my own biases and conviction, the single most important transition from what I like to call the first generation of DCI to the second or the next generation of DCI is the ability to reason about spatiotemporal execution of distributed applications. We are barely able to use distributed infrastructure in the fully distributed mode, or as I remember said, the collective utilization mode. But where we do, we often do it without an understanding of what performance am I likely to get from this collective whole? Where exactly will my workload or my distributed application end up executing? So the ability to reason about spatiotemporal execution is for the most part missing. So going back to the point about applications being, distributed applications being fragile, as I was transitioning to LSU, I worked on thinking of a very important problem in computational chemistry and computational biology, namely the translocation of polymers from one side of a pore, and this pore could be an artificial pore. It's obviously a naturally occurring pore, alpha-hemolysin in the human body, and the translocation of this polymer from one side to the other. The way most people had done this was very long simulations. Actually, people here at the Beckman, Klaus Schiltron's group pioneered some of these simulations. But what Klaus's group did was run these as single, very long simulations. And well, with a lot of computing power, you can run, at that time, 2005, 512, 1,000 core MD simulations using NAMD. But obviously, the time scale of translocations very high. For those of you who think about these, approaching a millisecond, and you can well imagine how difficult it is to run such a large molecular dynamic simulation leading to close to a millisecond. So what we started doing is that, are there non-equilibrium algorithmic approaches that would enable the translocation properties, primarily the free energy profile along the axis, to be recomputed in a wall clock time less, obviously not less computing time, but in a wall clock time that would be less. And I developed using some physics algorithms known as Jarzynski's and other approaches, a algorithmic approach which demonstrated that if you use task-level parallelism or distribution, you can actually recompute the translocation profile in very highly reduced points of time. And in a way, this was appreciated by the supercomputing community conference with the analytics best paper back in 2005. However, and I think this was one of the reasons why Ed wanted me to come over to the CCT, because of some work that Ed had read about and we had talked about. I'm sorry to tell you, Ed, you probably hired me on exaggeration, because although we got the algorithms right, and we thought we could implement them and actually compute the full profile, we actually failed. We actually failed to compute the full profile, and we reverted back to a much more traditional way, where we ran these very large simulations, one after another. And eventually we got a lot of the science done, and this is a paper of mine which made it to the cover of one of the more prestigious chemistry journals. So we got the science done, but not in the way we had anticipated. And this is just one way of telling, and there are many reasons why this happened. I will not get into many of the reasons you will understand. There were trivial reasons, interoperability, for example. There were more complex reasons, data movement management. So many of the issues that we still struggle with. But here is a null result rising from a failed attempt. And if you ever want a failed attempt, please.
Yeah, I mean, just to drive that point home, it was a decade earlier when the I-Way occurred, when I was actually still at NCSA, at SC95, where we tried to do a massive distributed computation, and Ian Foster's group was part of that, and a lot of groups tried to work together, and in fact, it failed. It failed pretty miserably after people stayed up for nights, for months, and the NSF director was there and so on. But what emerged out of that was the Globus meta-computing toolkit at that time. And so it actually was a great success in the longer term. So I mean, that's exactly, I think, what part of your story is.
Exactly, that is part of the story. And thank you. That's a great way of thinking. I should have thought about that I-Way analogy.
Yeah.
So this was the second point. So now let me quickly move to the third part, which is the fact that we have the inability to reason about spatiotemporal aspects about our distributed execution. So no doubts, this is a great success. The Higgs boson they even cite the Atlas project, which in turn is, as many of you know, responsible for driving OSG and other efforts in Europe. And if anything, the requirements as the post-Higgs success is going to be greater. However, many of you will know that as these tasks are run, and they run in a way that people don't necessarily understand where they're going to run. Or more importantly, there is absolutely no matching of supply and demand. There's just running them and hoping that they'll finish on time. There's no quality of service assurance. And what we like to call in a different context campaign planning. Well, the campaign planning is devoid of actually any planning. And this is what I want to say, is that as you scale out, and many of you will see similarities to LSST and other projects here, where as you scale to massive amounts, the ability to start planning the requirements, execution requirements, very different from these, because I understand the more dynamic nature of responses required. Here, there's no need of a dynamic response. But the ability to plan the campaign, the computational requirements is critical, but is currently missing. We don't have models for how many CPUs do I need to aggregate, for example, to meet the workload requirements, or how much trade-off should I make in the expected time to completion. Okay, so with this, I guess I've given, and with some background from the iWay project, you get a sense of the context and the status quo that I hope you believe that whereas we've made immense progress, there still are many, many aspects where we're learning when it comes to architecting and deploying production DCI. This is where I then move on to talking about what have we learned in the last 10 years since the failure of that nanopore experiment, if you will. And if there's a single message I want to convey to you, it's that I think we are finally converging on an understanding of at least some of the base abstractions, models, and principles, and I'll try to discuss these. And then I'll try to show you that the theory, the conceptual advances are actually being put to practice to deliver science at the same scale as the failed nanopore experiment in a routine sense. Okay, so this is kind of a quick way of saying that this is what I think starts laying the seeds for the next generation of DCI. Remember, in my mental model, next generation is where we have obviously some of the less fragility, but importantly, the ability to start reasoning about distributed execution. Okay, and so the objective is what are the abstractions that will allow us to perform such to effectively utilize DCI. I won't actually get to say much about the models, but just I say that as a kind of a way to tell you where we need to go in terms of not just qualitative aspects, but eventually quantitative reasoning. Today I'll focus on a demonstration of qualitative reasoning. But all of this reasoning, all of these models should enable us to answer these set of questions, which I kind of have already highlighted in the context of the Higgs boson's workload, but should be possible not just for those very large, but when a chemist decides, should I run 100 molecular dynamic simulations today, or should I plan 10 over the next 20 days? Next 10 days. So that ability to reason extends from the big projects to individual scientists. And in all of this, the only hypothesis that I want to make is, and give a hand-waving argument of addressing, is given that infrastructure is dynamic, it's changing, distributed infrastructure by definition is, because it's an aggregation of a large number of distinct resources, they're going to come and go or be available over different timescales, and this collectively leads to what is called a dynamically varying resource pool. So if you've got all these applications, if you've got this dynamically distributed set of resources, at what level should you start developing these abstractions and these capabilities to federate dynamically distributed resources? And the hypothesis is, as always, you can do anything at any level. The level that I propose we do this at is at the middleware level, which is not at the application level, not at the resource level, but at the level at which you can get information both from the resources, so works over heterogeneous set of distinct resources, as well as at the application level, so works for a broad range. In some ways, that is the raison d'etre of middleware, to act as that neck of the hourglass. So you've got a range of applications on the top and a range of heterogeneous infrastructure at the bottom. And as I said, this is the only kind of hypothesis part of it as to why. And lots of details in the interest of time. I'll just try to get to the punchline, is that what you need is to be able to couple dynamically changing resource state with possibly adapting applications, if not naturally, then to be adapted. And given the heterogeneity of resources, given the large range of application criteria, you want a way in which you can synthesize this information at the right level. This in turn opens up a whole set of questions. What kind of information are we talking about? How do you expose the information? What is the reliance on the quality, i.e. how lagged is the information about the resource? It opens up a plethora of research issues. I don't want to talk about those, but just want to point out that the next set of slides is going to try to validate this hypothesis of integrated middleware through a series of examples. But I hope I've been able to at least sketch out the reasoning behind why it should be at the middleware level and not an application level concern, and definitely not a resource specific concern. Okay, so over the past 2 or 3 years, as part of some of the projects, we started developing the, if you will, the base components to test this hypothesis. And you'd ask, why develop some more abstractions? Why develop a application abstraction? Why develop a resource abstraction? Why not use the many capabilities that exist? And the idea is we're trying to integrate them, and this speaks as much to the tooling and the software aspects of our community, of the capabilities of our community, that there aren't easily integratable, easily extensible tools that are let us going to test these hypotheses at the scales we need to. So we set about, and this is work done with Daniel Katz at Chicago and John Wiseman at Minnesota. Daniel Katz is responsible for the concept of skeletons, captures the primary characteristics of distributed applications in a nice, simplified way, tunable way. And the resource bundles abstracts out many of the resource specific details and provides a, let's say, consistent interface to the information exposed. Again, lots of details there. Permit me to move on into the points that I really want to get towards demonstrating all of this coming together. So just 2 other very quick points here, namely the notion of execution strategy, which is something we've all talked about, but we're trying to formalize as the temporally ordered set of decisions that need to be made in order to execute a workload on a distributed environment. So a lot of this is currently manually done, and there's no ability to reason if I took decision 2 before decision 3, what's the implication, as opposed to, let's say, taking decision X before, let's say, another decision. So the ability to change the, address in a carefully structured manner the consequences of the decision in the execution process gets codified in different execution strategies, and obviously testing the performance implications. And the one abstraction that I want to talk about here is that of a pilot. So again, a concept that many of you are familiar with, but I'll just give you a quick schematic here. This is what we're going to use to federate a large number of resources. And so a pilot job, in a nutshell, is basically a container job that generalizes the concept of this container job or a placeholder job that goes onto a resource. It could be a supercomputing resource, it could be a regular cluster, acquires the large set of resources, and then allows the application to slice and dice those acquired resources and assign them to the tasks that need to be managed. Now, whether this is distributed set of resources or a single resource, these are all details that we'll come to, but the basic concept is the user submits not the regular job, a pilot job, which may go to 2 different distinct resources. The container job goes into queue, gets queued up, becomes active. Once it becomes active, Whether the user tasks are pushed there or whether the pilot pulls there, these are minor details, but conceptually you get the idea. You don't submit a single task directly to the queuing system or whatever the interface. These also work for cloud environments. You submit submit these these container jobs, which then give you control. So, okay, so what I now have, just keep this concept in mind as the mechanism to federate a large number of resources. And what I'm going to try to show you is a series of snapshots where we submit a large number of pilots on distributed infrastructure without knowing the predetermined size of these pilots, where these pilots are actually going to end up, and obviously, therefore, not knowing which tasks are going to end up on which resource. So that's what I want you to remember in all of the following quick snapshots, that we have multiple pilots, different colors, going on to different resources, but not a priori determined, and the size and the configuration of these pilots is also to be determined. So the dynamic execution and the federation of resources. So just to set the scale, we're talking about approximately 700 cores on a machine, so a total of 2,000 plus cores over exceed here. And what you're going to see is what I was alluding to as execution strategy, the ability to first submit the pilots, understand the state change, based upon the resource information, understand the configuration of the pilots, right? And then based upon the configuration of the pilots, the workload gets mapped there. So just bear with me as I talk to you about a single pilot being submitted. As the pilot becomes active, tasks get submitted, and now you suddenly see 600 tasks, small lines going into this pilot. Remember, 2 other pilots have not become active yet. And then this is just a representation of how many tasks have gone through this pilot. So this indicates the pilot level activity. This indicates, if you will, the individual tasks. We'll come back to looking at these scales. Excuse me. We'll come back to looking at the y-axis in a while. Okay. And then now you see a second pilot also becoming active in the duration that the first pilot was active. And then lo and behold, a third pilot. So what I'd like you to quickly notice is the fact that in this execution, 704 cores were determined based upon the resource availability at that over this duration. 704 cores were determined to be the optimal size for trestles. There was, in this interesting case, similar sizes on Stampede and Gordon, but although you did not know which tasks went where, thanks to this kind of reasoning, the execution strategy, you are obviously able to understand which tasks go where. None of this was a priori planned. All that the user said is, I have approximately 2,000 tasks that I need to get done. I want to run this on all of the exceed resources. I submit to, in this case, the execution manager. Lo and behold, the execution, although all dynamically determined, and therefore the user has very low complexity in getting started, has the ability to understand everything that's going on. Okay, so this sounds, hopefully, it sounds simple but encouraging enough to start understanding and asking what are the implications. So if nothing else, at this point, I'd like you to appreciate the conceptual clarity that arises, simplicity that the user has, none of the infrastructural complexity of managing many different resources comes into play here. No prior guessing as to which resource to use, which is going to be, let's say, the better of the many resources. And right now, even though the scheduling mechanism is trivial, it's just a pilot comes up, a task goes to, let's say, underutilized pilot, i.e. backfilling mode. We're working on more sophisticated data-aware affinity-based scheduling algorithms so you can get the right task to the right place given the data sensitivity or the data requirements. So, okay, so let me, I should have said this. So all this just shows us that the federation across different resources can be done and can be understood. So you should say, so what? And this is what I hope to speak to over the next few minutes. Lots of data here. What I want you to focus on is just 2 simple things, that you have the ability to determine how much, if you will, dynamicity in your configuration do you want. You can control which resources are utilized. You can control the size of the pilot. So there's, if you will, a knob of the degree of dependence. So if you're darn sure that you know best where your workload should go, then yes, your opinion should rule over. But the important point is the flexibility to decide. The second is that the work that the capabilities that I showed you in the previous slide are not confined to any one specific application type. They are valid as well for single core jobs, as well as, let's say, 64-core MPI-style jobs, and I'll give you demonstrations. What I want you to understand here simply is the fact that they don't even have to, on the upper two plots, that the tasks don't even have to be uniform in, let's say, the temporal dimension. So it's not that we took an artificial set of tasks. We took, let's say, some were uniform, some were broadly, longer running tasks, and these capabilities work. If you compare along the vertical axis, if you compare what we call early binding, some level of predetermination, to what we call late binding, complete non-determinism of the pilot configuration, i.e. fully dynamically determined execution strategy, what I'd like you to look at is the leftmost column, the time to completion, and basically it's showing you that the time to completion is systematically lower when you do the dynamic configuration as opposed to a priori determining where your tasks should go. And this is for up to 2048 tasks all the way down. Right? So that's a quick take-home message. And obviously, along this dimension, the second right-hand column, it's essentially the same, but now for much greater level of heterogeneity in the tasks. And just as an aside, greater the heterogeneity in the type of tasks, lo and behold, greater the impact of the dynamic decision making. Okay? Okay, so hopefully that starts motivating us, but it's not just the mean time to completion. So the previous slide was a bit of a trick. I didn't plot error bars. Now let's compare two slides here, two different cases where on the left-hand side, you are computing, in this case, for 2048, a large, different distinct number of bag of task sizes, so starting off as low as 8, going up to as large as 2048 tasks. And you can see the great variation, and one would argue that there isn't even a well-defined mean there. Note, not even a well-defined mean. I'll return to this concept later, to this point later. And now look at exactly the same configuration when you have a dynamically determined pilot configuration over, at least over this range of 8 cores to 256. These are not only well-defined, but also look at the error bars, right? And again, there's a lot of details here, but if you're wondering why it starts shooting up after 256, we're reaching finite size effects, and I'd be glad to elaborate on that later. But just as a take-home message from this graph, note the advantage of dynamic execution configuration as opposed to static, right? And I'll give you fundamental reasons as to why this is. I'm just giving you the phenomena. I could give you the causes. Just in case you thought that those were small one-off, those were collected over one whole year, the data on the previous plot. And this is taken from XDMod, where what you see is the total number of jobs that my group submitted in order to perform those graphs over the year 2014. And 36,000 jobs were submitted in that 1 year, essentially every day, every minute. And whereas 36,000 places us as the 12th most, if you will, prolific job submitting group, there's an important catch there. Remember, each pilot job could have up to 2,000 jobs in them, individual tasks, actually up to 4,000. And so I leave it to you to do the maths. But the actual number of jobs we submitted in that period of time, or tasks we carried out, has an upper bound of either 35 million independent tasks, or more likely, based upon my prediction, since I don't have the exact distribution of each of the pilot jobs we submitted, order 10 million, which makes us 20 times more than the largest number of jobs. It's just that because we're using the pilot job mechanism, we're able to reduce the fluctuation. And so this is a point at which I just want to say, thank you to the Exceed team. You may not have been aware, but I think you have been, throughout the past year or so, been supporting some of the largest distributed computing experiments running every day of the year, and I could not have done this without your help. And as I said, this is just trying to show you the capability of building an infrastructure that responds to these new modes of execution. I'm not getting to the point where I will try to tell you how much I can predict, or how much we can predict what's the expected runtime going to be. We're still there. There's a lot of discussion that needs to happen. There's a lot of thinking that needs to happen. But the one thing I want to lay here is something I'm particularly excited about, is something what I call the capability model, whereby I'm just saying we're trying to think of what is the aggregated capacity in a time-dependent manner of all these resources put together. So not predicting, but just coming up with some well-defined function that is time-dependent, and then using that characterization of the resources to start doing the dynamic configuration of the pilot jobs. And initial indications are showing that there's going to be even more improvement, both in the quality, that is the variation, and obviously in the absolute mean. So in a way, what I think I can convey to you as a nutshell is we've demonstrated, and I think for the first time at the scale, how to federate resources, but we're still trying to get the rigor behind which resources to use, what configuration, so on. So some of the principles, the models underlying those principles are still works in progress. But this raises a very important question. That is, can you start architecting DCI for specific performance and requirements? And if you're thinking of what should the infrastructure for LSST be, or SCA, or whatever it might be, this is a critical question, and especially arises in the context of the Atlas project, where I'm now working with them to answer precisely this question. If they have 2 orders of magnitude more tasks and data, what kind of resources should they have? So can they have, for a given quality of service? So can you architect DCI for specific performance and requirements? And whereas the answer to that is obviously we can't, I hope to show you some glimmers of the first incremental, but first steps in that. And so you've seen the difference between the fluctuation and the so-called average. And if you think about what this graph is telling you, other than the fact that it's essentially flat over, let's say, tasks, the time to solution for tasks is essentially the same, going from 8 cores all the way, 8 tasks to 256. Non-trivial in of itself, that by using this dynamic execution mode, you've essentially removed a lot of the variability, as long as you don't decide in advance where this goes. But turn this question around on its head and say, we were designing a campus, or a bunch of campuses we're trying to get together, and trying to ask the question, which 3 campuses, how many campuses should we federate to in order to provide a quality of service for molecular dynamics tasks up to this size? Well, this is starting to give you some of the ability to answer those questions. I hope you see that. And again, there's obviously a lot of degrees of freedom. This is subject to a specific scheduling capacity, but our infrastructure allows you to bolt in any scheduling capacity, and thereby extension, possibly any policy or economic mechanism, right? The next thing this should tell you is, okay, I just talked about 3 campuses or 4 campuses getting together and asking how we might federate, but there's something more possibly profound. If I was trying to design an execution management service for the whole of Exceed, would some of this concept actually work? And I'd like to argue that it would, even though I don't have proof right now, but I'll try to sketch out the argument. You'd have, on the left-hand side, you have a discussion, you have the distribution of the actual workloads across the whole of Exceed over the past year. And you'll notice a very heavy peak around jobs of the size 9 to 64 cores. I posit, and I'd be glad to be corrected, I posit that a bulk of these 9 to 64 core jobs are resource fungible, i.e. they can go onto essentially any resource. If you have a job that's using 10,000 cores, not only are there a finite number of resources, but they're probably very tuned to a specific platform. But at the mid-range of 9 to 64, the degree in performance variation is likely to be smaller. And especially if you think of the fact that a bulk of these are community codes which have been optimized for any exceed resource or most exceed resource. This tells you that if you start designing an execution management service for the whole of exceed, you can, A, not only give kind of bounds on the response to users, in itself important, but you can improve the overall utilization of exceed. And now, why do I say this? We've done this experiment on Titan where me and my colleagues went from 90% utilization to 94% utilization. I've discussed with some people possibly doing this on Blue Waters, but think of this as an exceed-wide capability where the distribution of workloads, sizes and types is even greater, and therefore the dynamic space for optimization or backfilling is far greater, and you heard me reference that in the plots. You can, once you have a greater dynamic space to play with, you can actually start doing possibly more. So what we're hoping to do this year is mimic, can't do exactly the same number of tasks, but we're going to mimic this distribution and then start coming up with scheduling algorithms that possibly extend this to 256 and beyond uniform response time. Okay, so I've got about 10 minutes to 12 minutes left, so let me try to change gears very quickly and try to show you that this is theory, work, research, but a lot of these ideas are already being put to use in supporting science. And I'll show you not just any science, but science that I claim could not be done otherwise. Okay, and in order to, so one more thing I should say is that everything till now has been, if you will, the what of the research, the distributed dynamic federation of resources. Over the next few slides, I'm just going to show you the how, the implementation that must scale to support these kind of experiments, implementations that must be robust to the kinds of failures that this environment has, infrastructure that must be flexible to support the broad range of, if you will, workloads. And this is where the project that I've been working on over a decade, first was just called Saga, became part of the Cybertools project that was, again, run out of LSU. And then over the years, there's been important additions most notably in the form of scalable pilot jobs. So we call the suite of tools RADICAL Cybertools, which manage, in addition to heterogeneity, that's one layer, also provide many of the flexible resource management capabilities. Importantly, a design objective is to support all this research while supporting production science. So this would it would be unfair to come back and not to talk about Saga. I presume many of you may have heard about Saga, but underlying all of this, the fact that the heterogeneity is now an issue we can be blasé about, because eventually in 10, if not more years, we've at least mastered the heterogeneity that distributed infrastructure provides. And this is, again, something which began back pre-CCT days while I was still in London and Ed and Gab were still in Germany. And this, over the years, has evolved. If there's a time scale of reaching maturity and focus, this is one nice example. It takes about a decade to do anything properly and carefully. So I won't go into the details there. Just want to talk about pilot jobs, just in case you guys think I'm being dishonest here and trying to sell you a new concept in a new old concept in a new packaging. No. I know pilot jobs have been around since, well, some of you will remember the GRADS project, Ken Kennedy and all. They called it apples. But they've been called by different names, by different times, in different times for different purposes. And there's a whole lot of confusion in what exactly constitutes a pilot job. And the message I want to convey here is the role of theory in applied tool building. Just reference this paper where we sat down, we analyzed, surveyed all of these concepts which were under the umbrella of pilot jobs, but not always called pilot jobs, not always doing the same thing. And then we had to come up with a conceptual model for what constitutes pilot job, not normative, but at least a minimal concept, a minimal model of pilot jobs. So again, in underlying these implementation, it's not let's just go build a tool because we can build one, but it's a tool that embodies research as well as is a implementation of the research, right? So why the focus on pilot jobs? It's obviously the conceptual basis for, hopefully you've seen dynamic resource models, but in many ways, this goes back to an explanation of the lack of ability to plan your execution in advance, i.e. therefore the need for dynamic decision making. Lots of details here, and I was discussing some of this with Bill Kramer yesterday, where if you try to predict the queue waiting time, we've got some theoretical work that shows predicting is completely futile because it could be borderline chaotic. And this is just a way where we did some analysis going back to Rich Wolski's BQP of the actual predicted time versus the actual time for different load utilizations on different machines. And you can see that when the machines are not loaded, well, your prediction's fairly good, but as soon as loads reach a certain value, when you need the prediction, well, I think it might be fair to say a bit of hell does tend to break loose. Okay, so if you can't really predict your appropriate size in advance, well, if you can't beat them, join them, and so you might as well respond to the right, to the configured resource information. And that's what some of this pilot job allows you to do, rather than say, I want to run my jobs on 128 cores, you try to be, if you will, dynamically configured. But there's a lot more. It enables this breaks down the distinction between the so-called HPC model and the distributed computing model, as well as the high throughput and high performance model, and as a consequence of supporting very large scale task level parallelisms. And what I want to very large task level parallelism. What I want to end by is to try to show you how exactly this concept that I've introduced to you in a distributed computing context is enabling new methods on purely HPC resources, and thereby the claim that this distinction of HTC versus HPC does break down. So here's the headline. A lot of this was picked up by, well, NSF as well. This was the work I'm about to say was done in the context of HIV, but also by the popular press and others, where we actually showed you can do a large study on HIV drug resistance. So the big problem in all of this field is how do you utilize the resources that you have? Should you utilize your resources such that you run one very long simulation, or should you run many smaller simulations? So that's an issue of assuming you can do either or, which one should you do? And in some ways, this is a serious schism in the community. People don't realize which is better, which is going to be better bang for the computational buck, in the sense, given the finite amount of computing, which of these should you do? So this is the grand challenge problem, and this has many manifestations. Some of you will know of replica exchange as one of the sampling approaches, and this is really what the pattern that I call replica exchange is. You run a large number of ensembles, large number of replicas, they run for a certain amount of time, and then there's an exchange, and then they run again, then there's possibly an exchange. There are many, many perturbations on this. There could be a global synchronization where all of them come to a halt and then exchange predetermined partners. Or there could be no global synchronization, but predetermined partners. Or there could be something in between, that there's no global synchronization, but the exchange is also ad hoc and random. So many perturbations. But historically, what people have done is they've run all the replicas at the same time. And this has profound consequences. That basically means even if you run only a replica on only one core, the maximum number of replicas that you can run at any given instant of time is number of cores available. And this is true for all the replica exchange packages in Amber, NAMD, so on and so forth. And what we worked with some theorists show that actually, if you go from one dimension to two dimensions and higher dimensions, you can get better sampling. And there's a lot of details there. But lo and behold, as you go to larger number of dimensions, the number of replicas that you need increases as the power of the dimension. So A, you are historically confined to the number of cores being the maximum number of replicas, but you want to go to higher replica counts because you know that you're going to have better sampling. That's a very difficult situation to be in. And this is where the dynamic resource execution models come in. I'm going to show you examples of simulations where the number of replicas that are run are much greater than the number of cores available, and thereby they're able to go to much higher dimensionality. 1D, we've broken the 2D barrier, and we're about to break the 3D barrier. And 3D here is now exchanging along different dimensions. And again, this is work that's been published, and then some important challenging problems are being studied by these 3 dimensions. But the point here is, if you did not have this decoupling between the number of replicas and the number of cores, you would essentially be confined to the 1D model because of the exponential dependence on the dimensionality. We've broken that for a while. It does not change the solution time, but it at least shows that the methodological advances that the theorists have been working on have an infrastructural solution. Okay? Last example in the last couple of minutes that I have is something, again, which is fundamental to understanding the effectiveness of these biomolecular simulations. You do many, many simulations, and rather than just continue onwards, assuming all is hunky-dory, you would like to perform a checkpoint, and then you'd like to do some analysis, and then determine the next set of trajectories. And by the way, this pattern is also similar of ensemble Cannon filters and others. Obviously, here I'm talking about the specific case of molecular simulations. And again, there are variations in how the synchronization is done. There may be one single synchronization point, there could be different synchronization points. But the important point is the next set of trajectories, as you can see in this schematic, is determined by the outcome of the first set of simulations. So not all the replicas continue, only a subset of the replicas continue, hence the distinction from the replica exchange model. Again, so this is what is, again, a NSF-funded project called Ecstasy. Won't get into the details. I want you to look at the scale at which we're operating. Again, all the underlying infrastructure is the same, the pilot model. And lo and behold, now look at the number of replicas we're managing. 10,000. Now, obviously, this is zero workload. We're just trying to see the number of replicas we can get to. And we're trying to run 10,000 replicas, the 10K, the rightmost. The 256 is we decompose them into 256 groups, and we run them on, in this case, 16 cores. So the important thing is notice the decoupling between the number of replicas and the number of cores. And you can see that there's a lot of detail, and I don't have time, but you can see that as you increase the number of cores for the same workload, no surprises, you obviously get a better response time. And where there's some infrastructure, we're still tuning this. This is work done on Stampede. But the point we're, I think, very confident of making very soon is as you go from 10,000 replicas to 20,000 replicas to 40,000 replicas, you can essentially solve this problem on constant amount of time, as a consequence of growing the set of resources that you're solving. Clearly I would say a holy grail. We've just begun doing this on blue waters. We're right now at the systems investigation level. We're trying to understand the different approaches to managing many, many jobs on blue waters. Okay. I won't speak to the DIPS project, but just wanted to say some of the philosophy is the same. In the interest of time, almost coming up, I want to give you a kind of a quick summary of what I hope I've conveyed in the last 45 to 50 minutes. First of all, I hope you recall that distributed computing, cyber computing infrastructure is characterized by spatio-temporal heterogeneity. And as the scale increases, the degree of heterogeneity increases along all the dimensions. This is fundamental to keep in mind because the approaches we're talking about arguably get better with degree of heterogeneity and not worse. I've hopefully conveyed to you the importance of tools that are not just tools, but have well-defined utilization models, have well-defined semantic models, the pilot job model being one example. And I've tried to show you that if you've got the right abstractions, in this case, a pilot abstraction for dynamic resource utilization, you can take the same conceptual view of execution on HPC resources as well as distributed resources. I think critical in my mind to being able to allow scientists to seamlessly migrate across different infrastructures. And in this case also, the fact that either you federate open science grid style resources or you federate supercomputing style resources, the model is the same. Remember how I began by saying the end of the first generation moving to the second generation where we should be able to reason. I don't know if we can reason about everything. As a matter of fact, I know we can't. And that's why I modestly say we're moving towards the next generation of distributed infrastructure, which we call the science of cyber infrastructure, the ability to reason infrastructure as a science. But I hope I've conveyed to you that what required heroic efforts in 2005 and earlier is, from the scales of the operations I've shown you, routine now. Routine, and we can do better. So it's not just we can do what we would try to do, but now we can go beyond and in a much more reasoned, in a much more scalable, flexible way. Note the difference between the ecstasy way of doing things, note the difference in the requirements of the ecstasy project and the requirements of the replica exchange, but the underlying tools were exactly the same, minor changes. So we started to program these differences quite easily, yet no reinventing the wheel. And this is a consequence of, obviously, the right abstractions and the right questions in asking the reasoning, but it's also a consequence of the implementations. And what I hope I've shown you at the ability of individual tools, we're hoping to engineer at the complete infrastructure level, so as we go from abstractions to quantitative models, hopefully engineer entire infrastructure to support these new methods. It would be remiss of me to not mention the people who actually make this happen. These are the real radicals, and with that, I thank you for your attention and patience.
Great, thank you. Time for a couple of questions. I have to say, unfortunately, the NSF didn't check with us before they decided to have a webinar that's occurring at noon. So some of us are going to have to go off and listen to that because it involves something we're working on for these regional data hubs. But maybe a couple of questions quickly.
You mentioned replica exchange as the kind of a prominent example where you used this pilot abstraction and distribution and so on. Are there any other MD methods or algorithms that also scale like that? Because there are variability in those things. In replicas, I think you can control some of the variability.
Yeah.
Please comment on that. Thanks.
So I think even within the replica exchange class of applications, there are several different types of replications. It's not a single algorithm, there is a class. And we've applied this technique to all of them, to at least 3 or 4. Asynchronous replica exchange, Gibbs sampling-based, regular pH, different dimensional constructs, temperature, ionic concentration, so a range of them. So I think what I present you is valid for the entire class. But to answer your question more directly, another sampling approach is the ecstasy approach, where you might have a diffusion map or a PCA-based reduction, such as a, what do you call them, collective variable as the analysis. And again, what I'm trying to say is that we've run these as specific kernels, and that's why I kept talking to you about patterns, because you take the pattern, you plug in specific analysis or specific MD kernels, and this works on AMBER, the entire suite of them. And so they're not confined to a given method, nor are they confined to a specific MD kernel. Okay.
Other question? Just given the time, let me just make a final comment. I'm quite inspired by this to think about what we as a center could begin to plan, for example, at the next supercomputing conference or something like that, that really pushes the envelope. helps us drive forward our own agenda as leaders in the industry here, in this computational science industry, I would say, to figure out how we can pull the center together around these kind of things. Because you push the edge, and then as Shantenu is showing, a few years later, it's something that people are doing routinely to do their science. And it's really very inspiring. So let's thank Shantenu again. Okay, thanks.